So yeah, today I'm going to talk to you about how I made a genetic algorithm play Risk. So yeah, let's go on with it and do some risk analysis. I've structured the talk a bit like this way. First, since I guess many of you have played the game of Risk, but maybe not all of you, it might be quite a long time ago. First, I'll give you an introduction to the game of Risk, just to very quickly go through the game. Then I'll talk to you about how I implemented Risk in Python, and I'll show you the code. Then I'll give you an introduction to genetic algorithms, and finally I'll show you the results of that algorithm. So about the game. It was invented quite a long time ago. First time it came out, it was actually not called Risk, but it was called The Conquest of the World in 1957. But nowadays it's always known as Risk. And according to the publishers, you can play it with 2 to 6 players. I think it's more fun with 4 or more. And the playing time is somewhere between 1 and 8 hours. I can tell you, if you automate this goes a lot quicker. So, first of all, the game board. Typically, there's many versions, but typically it looks a bit like this. So there's what you see here. There's 6 continents. Each of them have a different color, and each continent is divided into some countries or regions, whatever. And so what happens when you set up the game? First, you gather some players. So, for example, you gather 4 players, and then you randomly distribute all these regions between the players. So I've indicated the players here with different colors, and then every player puts one army, which is indicated by the 1 in each of the circles here, places one army on each of the regions he owns. So then in the end, there's at least one army, or in this case, exactly one army on every region there is. And then all the players place a certain number of armies, which depends on the number of players on each of the regions, such that they all have, well, quite a few of armies on the game board. This is when the game actually starts. So people have placed the armies, and now the game starts. And then, so every player gets to play a turn, one by one, and each turn consists of 3 stages. First, there's reinforcement, then there's combat, and then there's fortification. So first, in reinforcement, the player places some additional armies. So they already got some armies on the board, but they get a few more. And so the number of armies they get to place depends on a number of factors. So for first, they get 1 army per 3 territories they own. And then there's some bonuses for owning a full continent or having some set of reinforcement cards, which I'll not go into. Then in the second stage, they can use those new armies to attack neighboring territories. So they can take a number of armies and go into a neighboring territory and then attack a neighbor. The battle is decided using dice. I'm not going into that, but I can tell you that the more armies you have, the better your chances. And then, so if you conquer the territory, then the territory will be yours. You will get a reinforcement card. And then, well, you can keep on attacking until you've had enough or until you ran out of armies. And then, in the final stage, fortification, so you can use any armies that are still on the board that you haven't used up for attacking and move them around to another territory. You can do this only once. You can only take one region and move armies to a neighboring region. You can move as many armies as you like, but just between those 2 regions. So that's it. This is how the game is played. But of course, well, we need to know how a player wins. Well, that at the beginning of the game, each player is assigned a mission, and by completing this mission, the player wins. Missions are, well, vary between things like conquer Africa and North America, or any number of continents, destroy another player, or conquer at least 24 territories. Those are these regions. There's quite a few more. We'll get to these later. So that's the game of Risk. I guess most of you sort of get an idea what the game is about. So let's have a look at how this looks in Python. So I built a framework that handles all these aspects of this game, and it consists of 5 classes. So first of all, there's the board, which handles all the armies that are placed on the game board. Then there's the cards, which handle the reinforcement cards of the player. Then there's the mission, which describes the mission of the player. Then there's the player itself, which needs to make decisions on how to play. And then finally, there's the game, which keeps track of turns, contains the board, etc. So let's have a look at these. First, let's have a look at the board. So immediately when initialized, we have to tell it how many players are there, and then it randomly distributes the territories amongst the players. So for example, if I say B is board.create, number of players is 4, then I get a board for 4 players. Then I can plot the board using a method called plot board, very easy, and then it will show you exactly what the state of the game is, just like this. And like I said, the regions have already been distributed among the players, and 1 army has been placed on every territory. It's fairly easy to manipulate the armies on the board. So for example, I can just take any territory 0, and say, well, this is now owned by player 5, and then set the number of armies on that territory to 15. And then you see there, right in the middle, there is a territory owned by the black player containing 15 armies. Of course, that doesn't really make sense in a game with 4 players, but it's fairly easy to do it. That's what I want to show. Then, well, the board is also aware of the layout of the territories, which makes it easy to just, well, for example, think of all the attacks you can make. So for example, if you just ask the board, what are the neighbors of territory 0, then it will just tell you, you get a list of all the territories, players, and the armies on that, on those territories around territory 0. This means that it can also handle attack moves using this. So for example, then I can tell it, I want to attack from territory 0 to territory 21 with 3 attackers. And then you can see, once you plot the board, that in this case, he was actually successful and he managed to take another territory. The board also rolls the dice and just handles all of that, so you don't need to do all the dice rolling and figuring out who won. So then there's the missions. So I made a missions function that returns all the missions for a given number of players. So the missions actually depend on the number of players because, well, like you can see at the bottom, there's also missions that say eliminate another player. And of course, these players need to be actually in the game for the mission to be there. So these missions, you can get them using this function. And these missions are actually aware of the player they're assigned to. So first of all, if we just take a mission, it's the mission that says conquer Asia and South America, and then it's unassigned. And then we can assign it to, for example, player 0, and then it's assigned to red. And then the mission itself can evaluate whether it has been achieved. And you can just say, okay, mission evaluate with the board. This is the board, and then it will return, at the beginning of the game, it will return false, of course. Then there's a special case, of course, when a player is to kill himself. So suppose we have the mission eliminate the yellow player, and then we assign this to yellow, then it turns into the fallback mission, conquered 24 territories assigned to yellow. So all of this is handled inside the game. You don't have to care about it. And then, of course, well, the most important part, there's the player object. A player object is required to have 4 methods. So there's the reinforce method, the attack method, the fortify method, and the turn in cards method. So the first 3 methods handle the first 3 stages of the game. So the game takes the player object, then calls each of these methods when it's this player's turn to do exactly that, and then the player object should return what it wants to do. The turning cards method has to do with the reinforcement cards. I'll not go into that. So now I've showed you how what the classes look like. Let's go through a whole game. I've implemented some random players which can play the game, but absolutely randomly. So every time It randomly decides what to do. Let's see what happens. So first of all, we create a game, and we take 4 random players. We put it inside the game, and then let's show the board here. Like you can see, it's maybe a bit difficult to see here, but there it shows some statistics on the game. So on the top left it says pre-game, and the bottom left is it shows which players are in the game, how many territories, and how many armies they have. So then the first stage of the game is to place the armies on the board. So first of all, we can say game initialize a single army, and then every player places a single army on the board. And you can see that for every player there's exactly 1 circle that has a 2 inside. So they placed an army. Now they can place armies up until they each have 30 armies on the board, and it may be a little tedious to call this thing 20 times. So there's also a method that says just initialize armies, and that handles all of it. So then this is the game board. All players have placed their armies, and now it's time for the first turn. And it says in the top left, turn 0, red. It also mentions the mission of this player, namely it's eliminate the blue player. Then, well, it's red's turn. First, red can reinforce. If you look closely to this board, you can see that red actually placed 3 more armies on this board. And then the next stage is to attack. And here, all that happened is, I realize it's very difficult to see if you're not really into looking at the game and watching what happens exactly. But what happened here is that red attacked that territory there, and yellow lost 1 single army, and then red randomly decided to stop attacking. And then he can fortify, and I think he actually fortified, I don't know where. But like I said, this is all random, so it does anything that it can do. It just looks up a list of all the things it can do and picks one. And then, so once that is done, we call next turn, it's a turn of blue, and then, well, this is the state of the game. So we can also use the play turn method, which just handles a full turn. So now this is what the board looks like after blue had its turn. Of course, we can keep doing this, but it gets a little tedious. So let's speed this up. Let's do this 10 times. We see that red is doing fairly well. And then we can just loop until the game has ended. And then we see that red has indeed eliminated the blue player in the end. Okay, so that's a game. Now let's get into genetic algorithms. So first, what is a genetic algorithm? It's a machine learning algorithm based on evolution and natural selection. So why would I use it? Well, it's fairly easy to use with little knowledge of the problem. I mean, I know the game, but I don't know exactly how to play it well. And it's fairly robust against noise and having many dimensions, because of course there are very many dimensions here. So first, let's take a very simple example. Imagine we're trying to solve a puzzle, and the puzzle contains or the solution of this puzzle is a 16-bit string. So for example, the one I show right here. And what we can do to solve this puzzle is we just, if we take a candidate solution, so any string of 16 bits, and then there is a function, a hypothetical function that tells me exactly how many of the bits are correct. So in this example at the bottom here, this function would yield 7, telling me that 7 of the bits are correct. Of course, this is a problem that you can easily brute force, but that's not the idea. So what we could do here is we could just randomly generate a few solutions. In this case here, there's 4 solutions, and if we apply this function on them, we get a result. So the top 2 have 9 bits correct, and the bottom 2 are much less good. So of course, we could generate more until we get the right answer, or we can be smart about it and combine the best solutions. So we know that there's 2 solutions that have 9 bits correct. I showed them here again, and I've made one red and the other blue just for illustrational purposes. And then we split these up and paste them together to form children of these 2 solutions. So what then happens is, for example, I take the first 8 bits of the blue one and then the last 8 bits of the red one, and then I get a solution that is much less good than the original 2. But if I take the first 8 bits of the red one and then the last 8 bits of the blue one, I get a solution that is much better. So using this method, we can take 2 solutions and create solutions that might be better than the original ones. Another way to improve any of these solutions is to just randomly mutate it. So for example, we could flip one of the bits. So if we take this solution that we got before, that was the best solution we had, and then 4 times randomly flip a bit, then we get 4 solutions that might be better or might be worse. In this case, we get 2 better solutions and 2 worse solutions. And we can keep doing this, combining solutions and then mutating them until we have found the best solution. And then, well, in this case, of course, the best solution is the one where 16 bits are correct. But in the case of a game of Risk, the best solution is, well, a player that always wins. So in short, a genetic algorithm requires a random initial pool of solutions. Of course, if you already have a pool of solutions that are better than random, you can use these. Some evaluation function, a combine method, and a mutate method. And then you just need to loop the combine and the mutate until you're satisfied. So now let's think about a genetic algorithm for Risk. How would you do this? There's a little problem, because like in the example before, we had these solutions and we had an evaluation function that tells us exactly how good our solution is. It says 9 or 6 or 12, and then I know 12 is the best. But of course, suppose we have 4 Risk players, player 1 through player 4, then which is the best? I don't have an evaluation function that tells me exactly how good this player is. Of course, we could have these players, all these 4 players play a game. So we have 4 players, we play 1 game, and player 3 wins. Then it might well be that player 3 is the best. We can do this a few more times, and then we might see that in the first time, player 3 was just lucky. So in the end, maybe player 1 is even better. So this is doable. If we have just 4 players, we can just have it play 8 times or something, and then take the player that won the most times as the best player. But what if we have 8 players? We cannot have 8 players play a single game together, because the game only supports up to 6 players. Of course, we could have players 1 through 4 play a single game, and then players 5 through 8 play a single game, but then we would never know whether player 1 is better than player 5, because they never had any interaction between them. Now, of course, we could play games with all combinations. But of course, if you have a player pool of 100 players, that would require millions and millions of games, and that just doesn't work. Luckily, there's a solution. The solution is TrueSkill. According to Wikipedia, it's a Bayesian ranking algorithm developed by Microsoft, and it's actually used in the ranking of players of Xbox online games. So it works roughly like this, and I stole this from Vincent's blog. So suppose you have 2 new players, then you create your prior knowledge of these players on a scale from left to being very bad to the right to being very good. Then you know nothing about them, so they must be somewhere in the middle, probably. So your distribution of their skill will be quite wide and centered in the middle. Now suppose that player 1, top player, wins, then it must probably be better than player 2. So your posterior, after the fact that player 1 wins in a game against player 2, is that the distribution of player 1 shifts a little bit to the right, and the distribution of player 2 shifts a little bit to the left. If, in fact, player 2 wins, then of course it's vice versa. The distribution of player 1 shifts a little bit to the left, and the distribution of player 2 shifts a little bit to the right. Now suppose that player 1 is very good. We already know that. And player 2 is new, so we don't know its skill. Now, if player 1 wins, well, of course we expected that. Nothing's changed in our knowledge. We still don't know. We already expected player 2 to lose, so we still don't know anything of the skill of player 2. And we already expected player 1 to win, so it does not change our knowledge. But in fact, if the new player, player 2, wins in a game against the very good player 1, then we know it must be fairly good, like it shows here. So if you want to use this, you can just install the TrueScale package. It's fairly easy. And well, using it just goes like this. You can make a TrueScale rating, and any TrueScale rating starts with a default score of 25. And then, well, if you can have them play a game. So for example, here you can see that player A and B before had ratings of 25, and after, once player A won, it has a rating of 29 versus 20 for player B. We can do it vice versa, or we can keep playing games after this. So if player A wins again, then its skill increases a little bit more, but not so much, because we already knew it was better than B, and the skill of B decreases a little bit more. Of course, then if player B wins, then it makes a big leap, because we thought before that player A was better. What's nice is that TrueScale can also handle multiple players in a tie. That means in the game of Risk, if we have only one winner, then player 3 through 4 are in a tie, all are losers. So using this, we can evaluate players of Risk. We can just have them play random games between each other, have TrueScale make a ranking, and then in the end, if we have 100 players, we can just take the top 10. Now, we just still need a player that plays Risk, a genetic Risk player. And so, as said before, the player needs to implement Reinforce, Attack, Fortify, and Turn in cards. And of course, we need a player that we must be able to mutate the player a little bit and combine it later. So first of all, let's think of how to pick a move. The easiest way is just to create a list of all possible moves, rank these moves based on some criteria, and then pick the top ranked move. For example, if we want to place a reinforcement, then, well, as far as criteria, we could, for example, define some territory ratio. So for every territory, we would calculate the number of hostile territories around it, divided by the total number of territories around it. And we could also define some criteria, mission, whether or not this territory is relevant for the mission of the player. So for example, if your mission is to conquer Africa and the territory is in Africa, then yes, it's relevant. So for example, suppose we own 6 territories, we must place a reinforcement, then we can calculate this territory ratio and this mission criteria. And then we define a reinforcement rank, which is basically the territory ratio times some weight plus this mission criteria times a weight. And suppose we set these weights to 1 and 2 respectively, then we can calculate this reinforcement rank for each of the territories. And here we see that the reinforcement rank for territory 18 is the highest. So we place our new army on territory 18. So how do we pick the weights? Of course, we do that with a genetic algorithm. So we initialize these players with random weights, we play many, many games, we drop the bad players, we combine and mutate the good players to create new ones, and then we repeat. So for example, if you go then look at the territory ratio. So for this territory ratio, we had this territory ratio weight. And then we initialize here in the top left graph, you see the initialized rates. So here we have a couple hundreds of players, and each of these players have a random weight between -25 and 25. And then after one iteration of playing, so we let these hundreds of players all play games, and we rank them using TrueScale. And then we take the best players, and we drop the bad ones, we take the best players, combine and mutate them such that we again have as many players as we started at. Then that's what we look at iteration 1, at the top right. And we already see that players with a higher weight here do much better. So we see that we are left with, well, in general, on average, a higher weight. Now, after 10 iterations, we get to the bottom left plot. And we see that basically only players with a positive territory weight are left. And then after iteration 40, it all centers around 15 or so. But so what does it mean to have a territory weight of 15? Well, of course, you have to normalize this against something. So that's why, for example, for the mission weight, I normalize this. I say it can only be either -1, 0, or +1. So this means in this case that the number of territories around a territory that you place your army on is 15 times more important than whether or not the territory is relevant for your mission. Of course, this makes sense because you're not going to place any armies on a territory that doesn't have any hostile territories around it. But also, in general, just if you have more territories, then you're more likely to win. And then in the end, if you do well in combat and ignore your mission, in the end, if you have all territories, then you won anyway. So I defined these 5 criteria for the reinforcement. First of all, do I get a bonus? So is this territory part of a complete continent that I own, and do I get a bonus for this continent? Secondly, similar, but if I do not own the full continent, then there's the mission value, then there's the army vantage, so the number of hostile armies around this territory versus the total number of armies around it, and the territory vantage, the territory ratio that I talked before. So this looks like this. First, we start with a random distribution. After one iteration, it goes a little bit to the middle. And then after 40 iterations, you see that it's actually, it goes negatives. That means that you better not place any armies near very large hostile troops. That makes sense. So for the direct bonus, we also see that this goes to a negative, a very negative value. And also that makes sense. Because so the direct bonus means that a territory is part of a continent that you fully own. That means that probably no one is near there, so you shouldn't place armies there. So this, to me, this means that the algorithm is doing what it should. So I've also defined all these criteria for attack moves and for fortification moves. And then in the end, this is what it looks like. We have, in the end, 25 weights that after 40 iterations have a certain distribution. So that's it. Are we done? Well, we're not. These weights, as you can see, these distributions, they don't show only very sharp peaks. In the end, you would expect them to, I guess. But these 40 iterations of running this algorithm took a couple of weeks on my laptop, and then I decided I needed it back for work. If anyone wants to know what it looks after 100 iterations, please just take my code and keep running, and then I'm very interested in the results. Also, of course, right now I use these weights, and these allow only linear combinations of all these weights, of all the criteria. And I guess that there must also be nonlinear effects here. Also, players do not look ahead. They're actually quite dumb, and they do definitely not adapt to their opponents. So, in conclusion, and I think I'm done early so that I'm by now not in between you and lunch anymore, we can play Risk in Python. I've made a genetic representation of a Risk player, and I've used a genetic algorithm to find better players. I took I took the best player from iteration 40 and played a game against it. It took me about 6 hours typing in which move I was going to make, and I lost. So N is 1, it's a good player. If you want to have a look at the code or more information, just go to our blog. You can find it right there. All the code is shared, so please improve. Thanks.